Hello friends, today we are going to learn crystal field theory in coordination compounds. So let's start with CFT, in short of crystal field theory. Basically we have learned in coordination compounds, metal combines with a ligand. So these metals, they are majorly elements of D block called inner transition or transition elements. So basically what happens is that ligand, which is either a negatively charged molecule, means having extra electron, or a neutral molecule having electron pairs, it provides it electrons into the valence orbitals or valence electron shells of metal, which accommodates them and form a coordination complex. Since the bond type of bonding involved here is kind of complete transfer of electrons, but sharing as well, because the ligand, it is transferring electrons, and metal, it is providing its orbital for occupation of these electrons, for occupying these electrons of ligands. It is called coordinate bond. Now we'll study what about CFT. What is basically all about CFT? According to CFT, these ligands, they are considered as a point molecules. According to CFT, ligands are considered as a point molecules in which there is electrostatic interaction. Please make note of this point: electrostatic interaction between metal and ligand. The metals, as we know, basically are cations having positive charge. In ligands, most of the time they are anions, negative charge, or neutral molecules. So according to CFT, there is an electrostatic interaction between metal and the ligand. So if the ligand is negatively charged, then it is considered as a point object. And in case of neutral molecule, it is considered as a dipole. As we know, all the d orbitals, they have 5 orbitals, in which 3 are along the planes. 3 d orbitals are along planes, and 2 d orbitals are along axis. So we can, there are basically dxy, dyz, and dzx. These 3 orbitals are along the planes. And if I consider an xyz axis, you can visualize this as a 3-dimensional axis, or for that example you can consider a corner of your room. Just hold one corner of your room and you will say that there is 3 planes, one along the x-axis, one along the y-axis, and one along the z-axis. You will say that these orbitals, they are along the xy, yz, and zx axes. So these are planar orbitals, and 2 orbitals, they are axial orbitals. They are dx square minus y square and dz square. So basically all these orbitals, they are having equal energy, which we call degenerate orbitals. So when all the orbitals of any shell or subshell is having equal energy, then those orbitals are called degenerate orbitals. Here comes the twist. In the coordination complex, whenever the point charge, let's consider this as an cation or metal, and consider these point charges as ligands. When they are at a certain distance or far apart from the metal, they are forming a symmetric structure around it. And while the structure is symmetric, the orbitals of the valence d orbital or the outermost d orbitals of this metal, they are having equal energies, which means they are right now degenerate. But as these point charges approaches towards the central metal atom, the degeneracy of these outermost orbitals starts breaking. And depending on the orientation of these point charges in space around the central metal atom, the degeneracy breaks. In the 5 orbitals which we have, it splits into 2 different orbitals, and which we call as T2G and EG orbitals. If these point charges, they approach from the planes or along the axis, depending on that, it will split into 2 different orbitals, T2G. So T2G is having all the orbitals along the planes, dxy, dyz and dzx, while EG is having all the orbitals along axis, dx square minus y square and dz square. So we can determine, or we can conclude here, that this splitting up of d orbitals, 5d or degenerate d orbitals, depends on the orientation of ligands around the central metal atom. If certain of these ligands approaches from the planes, then that will break first into lower energy, and the axial orbitals will break into higher energy. Similarly, if this configuration changes, then the splitting might be like this: degenerate orbitals, we have EG of lower energy and T2G of high energy. So now the orbitals along the axis will be having lower energy than the degenerate orbitals, and orbitals along the planes will be having higher energy. So one by one we will see how the filling up of electrons on all these newly formed orbitals, or which we call splitted orbitals, are done. So orientation, there can be 2 types of orientation. Basically we have octahedral complexes and tetrahedral complexes. For octahedral complexes, the transition will be into T2G of lower energy and EG of higher energy. For tetrahedral, T2G of higher energy and EG of lower energy. Okay, this was one point. Now another major factor which determines the crystal field is number of valence electrons, or number of electrons in the d orbital. We have 2 types of electrons: d4 configuration or d6 configuration. We'll look for the octahedral d4 and d6 configuration one by one, and you will try on your own configuration for d4 and d6 in tetrahedral complexes. Now we'll move on to the energy diagram for the octahedral splitting in crystal field theory. So there are certain terms which I'll be using. One will be delta O, called octahedral splitting energy. One will be P, called pairing energy. One will be barycenter. Another one will be T2G, EG, degeneracy, splitting, etc. So please be focused on these terms, and then we will look ahead after them. So first of all, as we know that our metal, or the cation, the metal central atom, it is having lower energy with all its orbitals having equal amount of energy, since they are called degenerate orbitals. Now as the ligands approaches the central metal atom. The distance between the central metal and the point charges, since we are considering the ligand as a point charges or a dipole, and here the negative part of the dipole, in case of neutral molecules, the negative part of dipole will approach the central metal atom. Please make note of this point. The negative part of the neutral molecule will approach the central metal atom. As the distance between the metal atom and the negative part or point charges will lessen, there will be change in energy. As you know, energy is inversely proportional to the square of distance between two point charges. The energy will change. But since the change in energy will be equal for all the orbitals, and the energy will rise, still all the d orbitals, they will be having equal energy and they are still degenerate. Now comes a point when the degeneracy will break. At this point, the ligands from the planes will be more close to the central metal atom as compared to the ligands from the axial point. And now comes the splitting up of orbitals, splitting up of d orbitals into Eg and T2g. The energy required for splitting is called octahedral splitting energy, represented by delta O, or the energy difference between the newly formed T2g and the Eg orbitals is called delta O, octahedral splitting energy. But since the number of orbitals and the orientation is different, there will be different amount of energy change compared to this. The T2g will change by, value of T2g orbitals will decrease by 2/5 of octahedral splitting energy, and value of Eg orbitals will increase by 3/5 of splitting energy. The positive sign represents the increase in energy and negative sign represents the decrease in energy. This is how the splitting of orbitals will take place. There are three orbitals, dxy, dyz and dzx. Similarly, here we will have two orbitals, dx square minus y square and dz square. To make a diagram more clear, along the x-axis we will represent energy. So right now all the degenerate orbitals are degenerate, and it is here the symmetric structure of the compound is maintained. As the ligands move more close to the d orbitals, the energy will be changed, and the energy of the electrons in the outermost d orbitals of the metal atom or central metal atom will increase, but still degeneracy is maintained. Make note of this, degeneracy is still maintained, but as the symmetric point structure between the ligand and central metal atom breaks, the splitting up of d orbital takes place, and this is called crystal field splitting. Hope you are understood till this point. Now we'll consider one point. We'll see how the electrons are filled for a D4 molecule or any compound. Octahedral D4 means having 4 electrons in the valence d orbital. Okay, so there is a point called delta O and another parameter called pairing energy. Since both these terms are energy, so we will compare them. If in case delta O is greater than pairing energy, okay, so there is a question arises, what is pairing energy? Before proceeding ahead, we'll look at this term. What is pairing energy? Pairing energy is the energy released when two electrons which are present in two different orbitals. If electrons who are present in two different orbitals, let's consider this or d orbital, and one electron each is present in one orbital of this d shell. If we move one electron, making them singly paired to double paired or filled d orbital, the energy released, energy required for this process can be called as pairing energy. So now we will see for a D4 complex crystal field, for a D4 having octahedral splitting energy greater than pairing energy. Okay, I'll redraw the diagram. You can also draw it along with me. So here is basically our central metal atom having 5 orbitals in it. All the orbitals are of equal energy. As the ligand approaches, the energy value changes. Now the d orbitals will be having more energy, but still all the orbitals are degenerate, means we haven't broken the degeneracy. Now as the point charges are moving along the planes and along the axes, the splitting up of orbitals will take place. This energy gap is called octahedral splitting energy. This will be Eg orbitals, this will be T2g orbitals, and in T2g orbitals we have orbitals which are along the planes, and in Eg we have orbitals which are along the axis. So here dxy, I will name them dyz, dzx. I will name it here as well, dx square minus y square and dz square. Now we'll see for a D4 having octahedral splitting energy greater than pairing energy. Since pairing energy is less, what will happen? Can you guess? In the filling up of electrons, first we will fill all the orbitals. As we know that during the filling up of electrons, orbitals having lower energy should be filled first. So we'll fill all the orbitals, making them singly occupied. This is our filling up of electrons rule. You must have studied Hund's rule of maximum multiplicity, Aufbau principle and Pauli's exclusion principles. Combining all them, first we are singly filling all the orbitals. Now we have one more electron, and that will depend on delta O and P, whether we need to fill it here only or we need to fill the next level. So if delta O is greater than pairing energy, in that case we'll take it to this position. Cool? Is it clear to you all? So we have filled the orbitals here. Now let's see what if delta O is less than pairing energy. Okay, now one more question arises. What's the spin of this complex? So since the number of electrons which are free or singly occupied is 2 here, the spin is low, and since the electrons are paired completely, it will be low spin complex. The complex formed will be low spin complex. Hope you are clear with this. I'll draw energy, and this point from where the splitting takes place, this is called barycenter. This is called barycenter. So it is low spin complex and strong ligand. This is also a point. This is how CFT helps us. It helps us to determine whether the ligand is strong or a weak. Since the pairing of electrons is taking place, it is a strong ligand. Now let's see for the conditions of delta O less than pairing energy for a D4 molecule only. For D4, delta O less than pairing energy. We are having, I'll redraw the diagram. Energy, all the degenerate orbitals. Now, as the point charges are approaching the central metal atom, energy will increase. Now there will be change or the splitting up of energy. This is delta O, octahedral splitting energy. The value of T2G will decrease by 2 by 5 of delta O, and value of EG will increase by 3 by 5 of delta O. We are having 3 orbitals, dxy, yz and zx, and we are having 2 orbitals, dx square minus y square and dz square. Clear till now? Now we are having 4 electrons. We will start filling them one by one. So first, same as earlier, all the orbitals are singly occupied, and since pairing energy is more, the remaining orbit electron will go into EG, and now you will find that all the 4 electrons, they are singly paired. So spin will be high. It is high spin complex. And can you tell me nature of electron ligands? Nature of ligands will be weak filled ligand. Nature of ligands will be weak filled ligands. Hope you are clear with this. Okay, so I have a question in mind. Can you tell me what is the magnetic character of this compound? Means since all the electrons are free, and as we have seen for a T4 with delta O greater than pairing energy, there are only 2 singly occupied electrons. And for D4 with delta O less than pairing energy, there are 4 singly occupied electrons. Can you tell me about the magnetic character? Okay, so if there are more number of singly paired or half filled electrons, in that case the magnetic character will be paramagnetic. And in case of paired orbit electrons, the magnetic character will be diamagnetic. Hope you are clear with this. Okay, so this was for D4. Now we'll see for a D6 complex. So till now we have observed that the crystal field splitting, it depends on the orientation, as I have explained you earlier, that what is the nature of geometry, octahedral or tetrahedral, and what are the factors. Result of that was the splitting up of orbitals. So I'll note down one thing: if orientation, then splitting of d orbitals, or I can even say transition, which is called commonly known as DD transition or T2G EG transition. These are the common name for splitting of d orbitals. So if the orientation, if it is octahedral, then T2G will have lower energy and EG will have higher energy, and if it is tetrahedral, then EG will have lower energy and T2G will have higher energy. Okay, next point was electrons in valence shell. As we have seen for D4 or D6, we will observe now. Okay, so let's see for a D6 complex. And one more thing was there, pairing energy, don't forget that. Now we'll see for a D6 complex, octahedral. Octahedral D6 complex. Okay, so again we'll redraw the energy diagram. It is energy. We have all the d orbitals degenerate. Now as the ligand approaches, the energy of degenerate orbitals increases. Now comes the splitting up of orbitals. So again, here it is delta O. This is T2G. This is EG. You must be able to label the diagram well now. This is 3 by 5 delta O. And this is minus 2 by 5 delta O. 3 orbitals on T2G side. 2 orbitals on EG side. Let's start with octahedral splitting energy greater than pairing energy. Okay. So now we'll have for D6 molecule. So we are having 6 electrons. Let's see that. All 3 singly occupied. Now what we will do? Since delta is greater than pairing energy, we will double fill all the lower energy orbitals. We will double fill the lower energy orbitals. So will there be any spin? No. It is zero spin complex or low spin complex. Okay. And type of ligand? Can you explain me? Yes. Type of ligand will be strong field ligands. So I can say no spin complex or strong field ligand. Okay, one more thing. What about magnetic character? Since all the electrons are pair, there will not be any kind of magnetic character or extremely low magnetic character. So we will have diamagnetic complex. Clear? Hope this is clear to you all till now. Now we will see for delta O less than pairing energy. Again, I am redrawing the diagram. All the d orbitals. Five d orbitals I have drawn. Now, as the orbital ligands approaches, the thing repeats. That is, the energy of d orbitals will increase. Now we will split, or we will say the transition of d orbitals will take place. This is again delta O. The energy difference will be minus 2 by 5 delta O. Here energy difference will be plus 3 by 5 delta O. T2G, EG, we are having 3 orbitals, dxy, dyz and dzx. Here we are having 2 orbitals, dx square minus y square and dz square. Okay, since delta O is less than pairing energy, so what will happen? And we are having 6 electrons. It is D6 molecule. Remember that, octahedral D6 molecule. First we will give them singly occupied. Now, since the pairing energy is more, electrons will be singly filled first. If the pairing energy is more, electrons will be singly occupied first. Remember this thing. If pairing energy is less, then electrons will be doubly occupied, and if pairing energy is more, then electrons will be singly occupied. Now we have one more electron, and that will come into this orbital. So we have one orbital which is completely filled, that is, they are having 2 electrons and all other are singly occupied. Clear? Since orbitals are singly occupied, I can say them as high spin complex. So they are high spin complex. And what is the nature of ligand here? The nature of ligand is weak field ligand. The nature of ligand is weak field ligand. And what about magnetic character? It is paramagnetic. Hope this is clear to you all. Cool. Okay, so we have now considered three factors till now on which this crystal field splitting energy depends. The three factors are orientation or geometry, you can say, next was valence electrons or d orbital electrons, next was pairing energy. One more thing comes, and that is ligand, the nature of ligands. Nature of ligand. It also determines the crystal field splitting, that is the value of delta O. Okay, so we will study about one more factor, that is nature of ligands and spectrochemical series. Spectrochemical series. So spectrochemical series is when the ligands, negatively charged ligands or the neutral molecules are arranged in the increasing order of energy, increasing order of crystal field splitting energy. Remember this term. When ligands are arranged in increasing order of crystal field splitting energy, in increasing order of crystal field splitting energy, the series is called spectrochemical series. Clear till now? Okay. Let's see few of the common ligands. So most is I minus. This is having the highest crystal field splitting energy. I minus, then will come S2 minus, then we'll have SCN. This is thiocyanate. SCN minus, Cl minus, Br minus, OH minus, oxalate, C2O4 2 minus, H2O, NH3, and in the end we have isothiocyanate, NCS minus. So this is all about spectrochemical series. Hope this is so. This is order of the decreasing order of spectrochemical energy or the decreasing order of ligands in crystal field splitting energy. So I minus is having higher crystal field splitting energy, which is also called CFSE, as compared to S2 minus, which is having furthermore as compared to thiocyanate, and the series goes on. In between, few more ligands are there, which you can learn in a later classes or in higher grades. Hope you are clear till now. Okay, I'll give you a diagram, energy level diagram for tetrahedral molecule, but make sure you fill it on your own, because this is a homework for you, and if you are able to fill it on your own, then this class you are able to understand this lecture very well. In case of any doubt, you can do reply us back in the chat section or in the comment section. So we'll draw a diagram for a tetrahedral. I'll just assist you with the diagram. After that, you have to fill the electrons for both D4 and D6 on your own. Keeping in mind the comparison of delta T. The crystal field splitting energy for a tetrahedral complex is called delta T. Okay. Keeping in mind delta T and pairing energy. So the diagram will be something like this. All the d orbitals having equal energy. Now here we have Eg on the lower energy and T2G the high energy. This energy gap will be called delta T, tetrahedral crystal field splitting energy. So we have 2 orbitals on Eg and 3 orbitals on T2G. This is the basic diagram or crystal field energy diagram for a tetrahedral complex. Now you have to fill this diagram for a D4 molecule and a D6 molecule. So we will have D4 and D6. Okay, and there we will have 2 conditions. If delta T is greater than pairing energy and delta T is less than pairing energy. Similarly, we will have delta T greater than pairing energy and delta T less than pairing energy. You can reply back the nature of ligands, paramagnetic characters, and nature of complex, high spin complex or low spin complex to us in the comment section. Hope the concept is clear to you and you'll be able to draw any crystal field diagram for any of the coordination complexes. Give if you have provided orientations and the number of valence electrons. Thank you. Do reply in the comment section.